So by now you've heard me talking about meaningful time and meaningful space. I'm going to focus here on the baseline of meaningful time. When we're trying to understand how watersheds, particularly intact watersheds, were able to produce a set of economic, social, and environmental values over time, rather than choosing today as our baseline, it's more useful to look back and understand how those systems functioned in a pre-industrial state. Oftentimes when I'm working with indigenous people in North America, we also refer to that as the pre-European contact period. And so in that period, which was spanning thousands and thousands of years, many generations of indigenous people were present on the landscape, and the major influence of change in those watersheds were natural disturbance. So, for example, if we're interested in understanding how an ungulate population that is dependent on certain kinds of forest at different age classes, how that would have performed over time, what we need to do is be able to simulate the conditions under which those ungulates would have survived, and their populations would have fluctuated and risen and lowered with changes on the landscape from wildfire, as an example. So what I'm going to show you here is how we use the ALCES tool to help us estimate or calculate the range of natural variation for a given attribute. So I've selected quite a large watershed here, so a 17,000 square kilometer watershed, and looking at wildfire. So drawn information from the literature to understand what pre-suppression, fire suppression rates would have naturally been in the ecosystems within this watershed. And then we use the ALCES model to simulate those natural fire events in small, medium, and large fire sizes within the range of frequency that the literature suggests would have occurred over time. And we do a number of different runs because depending on where you start and the age class of the forest and then how the fire rolls out on the landscape, you'll get different outcomes. So we allow the model to work fire randomly within a range of probability. We call that stochastic modeling. And so I'm going to just show you, oftentimes what I've been doing recently is looking at 4,000 years of simulation to understand that range of variation. I'm just going to show you 3 different simulations and the differences. So you can see here on my time slider in this watershed, it's back to 1810, pre-industrial time. And what we're showing here is the age class distribution of coniferous forest within this watershed. The redder it is, the older it is. And so you can see this is 100 years of simulation. And over on the right-hand side, here on my graph, we've got data points that are reporting out. I've asked the model to report them decadally. It's giving me the regional average age of coniferous forests in each one of these decades in this simulation. And up here you see this bar graph will change over time as we look at the different time steps, but it's showing you the age class distribution, the percent of the landscape that is in each one of these age class distributions. What's very handy is you can very easily export this as an image. A PDF document or a CSV file is my favorite because I like to export it into a spreadsheet and then work with that data. The same with this graph here. And of course we can export the timeline simulations of the maps over time. So I'll just get the model going here. We'll go back to 1810 and we'll look at this simulation, and you'll see how fires are burning on the landscape in different areas. And over time, the age class distribution of the forest is changing. And so this represents 100 years. And so what we often do is a set of these different assumptions, starting with different initial age class distributions, allowing the landscape to burn and establish a sort of a stasis condition, and then we forecast out 100 years worth of data, do that multiple times, and use that information to calculate a range of natural variation. So this is one simulation, and you see the shape of the curve over time, and you can see the bar graph changing over time over here as well as the map. So this is powerful. And then that's RNV simulation number 1. You can see over here I've chosen that. I'll then show you RNV2. So this is a different possible pattern and frequency of fires burning on the landscape. So you can see the shape of this graph is quite a bit different. And the spatial distribution and timing of fires burning on the landscape is different again. And then here's a third example. So of course I'm not going to show you all of them, but just to give you an idea of how this looks and how easy it is then to use this information as an analyst. And it's very resolute. I can stop this simulation, dig in here. I think for this very, very large watershed, I was working at 200 meter resolution. We can go down to 100 meter resolution, and I could look at a particular area. If this area between Squilax and Sorrento and Blind Bay, as you can see, may have been of particular interest, maybe for cultural reasons or locally for a specific species of wildlife. So we can see how those potential changes are occurring in a very resolute way.